Guys, in this question, we're going to take a look at applications of cross product to computing torque. So torque, the actual magnitude of it, the formula for the magnitude of the torque, so that would be, let me just, so usually torque is denoted by a Greek letter tau. And basically, it measures how much pressure, first of all, is applied to a point, and it's usually some kind of twisting motion. So maybe you think of a closing of the door, and so you're applying a force. So how much force you're applying, that the torque is going to depend on that, and also it's going to depend on the distance from the point you're applying the force to the point where the rotation actually happens. So think about if you are applying force to the door that, like, let's say the handle of the door is far away from the axis of rotation, and then it's going to be easier to close the door, whereas if you're applying the pressure very close to the axis of rotation, then actually it'll be harder to close the door. So the torque takes into that into account. So the formula for the magnitude of the torque is equal to the magnitude of the force multiplied by the magnitude of the distance from the point where the force is applied to the point where the object is rotated, and then multiplying by sine of the angle between them, so the angle between F and R. So one thing that to worry about here is the units of measurement. So torque can be measured is in Newton meters. So if the force is measured in Newton and then distance is measured in meters, then it would be Newton meters. But if it's, as in this case, foot pounds, then we have to make sure that the R here has to be expressed in feet. But what they say is that it's 10.52 inches, and that's not feet. So we need to convert that to feet, and we're going to divide by 12 to do that. So as you know, 1 foot is 12 inches. So that's going to be so the actual computation you have to divide by 12. There's one other thing here that is a little bit tricky. We do know the magnitude of the force is 9.9, so we can just substitute that. And so this is your distance on R or D, they call it, or D, whatever. Doesn't matter. But and then the problem is that this theta angle is not really this angle. So that could be kind of confusing because I said that that's theta and here it says theta, but it's really not. Because what we're trying to do is find the angle between the vector, well, let me draw like this vector right here, and this vector right here. Angle between the D that they call it and F is really this angle right here, and that's not that. So the connection between them is that they add up to 90 degrees because this is a right triangle. So this angle right here, that's 90 degrees. And so as you know, the sum of the angles is 180. So the angle that I'm looking for is the angle between the D or R, whatever you call it, and F. And that's really 90 minus 36. So our angle theta in my notation is really 90 degrees subtract 36 degrees, which is going to be 54 degrees. So finally, to find the magnitude of the torque, I need to find 10.52 divided by 12. Then I multiply that by the force, which is 9.9, and multiply that by sine of the angle. But again, the angle is 54 degrees. So if I were to use a calculator at this point, put it side by side. So that's 10.52 divided by 12 multiplied by 9.9 multiplied by sine of the angle. Now, you do have to make sure that the calculator is in degrees. So I got approximately 7.02 foot pounds.